Okay, thank you very much. Yeah, I will talk with the title, Explicit Construction of Exactly Unitary Designs. And this talk is based on the joint work with Yoshifumi Nakata in University of Tokyo, Takayuki Okuda in Hiroshima University, and Da Zhao in Shanghai. Okay. Okay. Yes, the plan of my talk is as follows. First, I will explain what is design theory. Then I give a brief survey on spherical T designs. And then we define the concept of unitary T design. And then we talk about the classification of unitary T groups, not design, T groups. This is a joint work with Navarro and Rizzo and Teep. And then explicit constructions of unitary 4 designs in U of 4. This is unitary group of dimension 4. This is joint work with Nakahara and Da Zhao and Yanju. And finally, this is the main result is the explicit construction of unitary T designs in UD for any T and any D. And this is a main result. And as I said, this is joint work with Nakata, Okuda, and Da Zhao. Then final remark. Okay, what is design theory? The purpose of design theory is for a given space M to find good finite subset X that approximate the whole space M well. If M is S n-1, the unit sphere in n-dimensional real Euclidean space, then such X are called spherical T designs. This is a definition of, okay. And what is, let me define spherical T design. This concept is due to Delsart, Gotthals, and Seidel, 1977. A finite subset X of the unit sphere, Sn-1, is called a spherical T design if the following condition is satisfied. Here we take F, any polynomial of degree at most T of variable x1 to xn, then f of x integral over the sphere divided by the surface area of the sphere is given by this average value of at finitely many point x. If this condition is true for any polynomial f of x of at most degree t, then it's called a spherical T design. Okay. And also, we can define so-called weighted spherical T design. Another name is curvature formula of degree T. And this time, we have a finite set X and weight function W, function from X to positive real numbers. Then this pair XW is called a weighted spherical T design, or curvature formula of degree T if this condition is satisfied. Namely, left side is the same integral of F over the sphere. The right-hand side is weighted average, namely sum of W of X times F of X for any polynomial F of degree at most T. So weighted spherical T design is a generalized concept of spherical T design. Now, let me quickly explain about spherical T design. This is a very brief survey. First, we discuss examples of spherical T design on Sn-1. The example for n equal 2, namely we have R2, namely usual plane, and S1 is a unit sphere, namely circle. Then T plus 1 vertices of a regular T plus 1 gone inscribed in a unit circle forms a T design. And the example of for n equals 3, the set of vertices of a regular polygon inscribed in S2 become a spherical T design for some T. But we have only 5 Platonic solids, and T is bounded by 5 for these regular polyhedrons. So basic question is, can we find spherical T designs for a bigger T in S2? This is a very simple question, but it's not so easy to answer. This is actually, it is possible, but not so easy. If n equals 8 or n equals 24, the 240 minimum vectors of E8 lattice forms a 7 design. And also 196560 minimum vectors of Leech lattice make an 11 design in S23. So there are many interesting examples. Okay, many examples of spherical T designs are obtained either as the following one of 2 ways. Take an orbit of a finite group G of real orthogonal group. And we have many examples by this. Also, if we have a lattice in Euclidean space Rn, then we take a shell. Shell is a set of lattice points which is of fixed distance from the origin. So in that case, x dot x is m is fixed. Then such set, if we normalize by 1 over square root of m, this vector becomes a unit vector. So subset of unit sphere. And this way, we have many spherical T designs from lattice. But if we just consider example coming from orbit of a finite group G or from a shell of a lattice, then in the case of A, all examples we know are bounded by T at most 19, in this case A, of an orbit of a finite group, and also by 11 if we take a shell of the lattice. And it is an interesting open problem whether T is always bounded by an absolute constant independent of dimension n in each of the above 2 cases A and B. This is an interesting open problem. Still, I think it is open. Okay. Now, let me discuss the existence of spherical T design on the unit sphere. Actually, we can show that there exist T designs on Sn-1 for any n and any t. This is a famous result by Seymour and Zaslavsky in 1984. And many proofs are known about this fact, but they only show the existence, and good explicit constructions are not yet known, but I will discuss about this later. The best existence result is due to Bondarenko, Radchenko, and Vyazovska. It's published in Annals of Math 2013. And that shows the existence of T designs with the sizes asymptotically the same order as the best possible bound. And in particular, if n is fixed, dimension n is fixed, T goes to infinity. This is the best existence result. However, what happens if T is fixed and n goes to infinity? This time, we don't know the exact result. It's still open, interesting open problem. And one remark is most of non-existence proofs use the continuous property of real numbers. So proof is very analytic or topological. A new existence proof was obtained by Zheng Tui, Jiacheng Xia, and Zuqing Xiang in the paper Rational Designs, published in Advanced in about 3 years ago. And number theory. And how about the explicit construction of spherical T designs? And some examples are known. For example, by Cooper-Bach, but this is just for n equals 3, and the size is very big. And for n equals 3, there is a result by Chen, Frommer, and Lang about 10 years ago. For t at most 100, they could explicitly describe example with size t plus 1 squared. This t is up to 100, slightly improved, but still general case is open. On the other hand, Zuqing Xiang, in his paper, Explicit Spherical Designs, which is to appear in algebraic combinatorics, gives a more general explicit constructions. And it is a very delicate question. What are good explicit constructions? And I think good explicit constructions are yet to be given. Okay, it is easy to see that if X is a spherical T design, then for any orthogonal transformation G, if we transform X by G, then it's again a spherical T design. Moreover, if X1 and X2 are spherical T design, then their unions is a spherical T design. So we are naturally interested in the spherical T designs of small sizes. And our problem is, are there any natural theoretical lower bound of the size of spherical T designs? And yes, there are Fisher type inequalities. And more difficult problem is for given T and N, determine the spherical T designs of the smallest size. This is a very important fundamental problem in design theory, but more difficult than the first question. So I will discuss first question first. Here is lower bound for the size of X, namely Fisher type lower bound for T designs. And this sum of binomial coefficient, if T equals 2e, T design, T is even, then this is lower bound. And if T equals odd, this is lower bound. This is called Fisher type lower bound and proved by using harmonic analysis on the sphere. And if equality folds in one of above inequalities, then X is called a tight spherical T design. And we are interested in the classification of tight spherical T designs. And actually, they are classified. If n equals 2, then X is a regular T plus 1 go. So we assume n is at least 3. Then we have shown many years ago that T is at most one of these numbers, 1, 2, 3, 4, 5, 7, and 11. And those with 1, 2, 3, or 11s are classified. But 4, 5, 7, it's still open. And there are some development by myself, Munemasa and Benkov, and then Neve and Benkov. But the problem is still open for T equal 4, 5, 7. So this is an interesting open problem. Okay, now we want to discuss unitary T designs. Okay, as I said, there are various design theories for various given space M. And when M is the unitary group itself, this is a continuous group, unitary group UD, then design theory there is about unitary T design. Here is a formal definition of unitary T design. A finite subset X of the unitary group UD is called a unitary T design if the following condition is satisfied. We take a kind of polynomial over unitary groups, take integral over unitary group, and this is normalized. The volume of UD is equal to 1. Then f of x is a polynomial, and then integral over UD is average value of f at finitely many point x. So such finite set x is called the unitary T design. And what is our polynomial f on the unitary group? And this is actually defined as follows. Polynomial over UD of R parameter Rs is a space of polynomials that are homogeneous of degree R in the matrix entries of, with respect to the matrix entries of U, and homogeneous of degree S in the complex conjugate of the matrix entries of U. The U are a unitary matrix. And then home UD RS is such space of polynomial in this sense. And when we consider unitary T design, we take this S equal R equal T and S equal T. So we consider home UD TT. Then for such function, namely polynomial f, this integral over UD is given by the average value at finitely many points of x. Then such x is called a unitary T design. So it's something very similar to spherical T design. Okay, the concept of unitary T design was started in physics, in particular in quantum information theory. And here are some basic literature on basic papers which introduced unitary T designs. And Gross, Andernatt, and Einsat. This is in physics paper, and Andrew Scott. And this is also in the physics paper. In mathematical point of view, Roy and Scott describe unitary designs and codes. And this is 2009. And there is interesting paper by Zhu, Kuhn, Grassel, and Gross. The Clifford group failed gracefully to be unitary for design. And I think in the next talk by Da Zhao, he will mention about this paper. Anyway, this is the start of the study of unitary T designs. And this was started in physics. Now, what are known in unitary T designs? First, unitary T designs in UD exist for any T and any D. Again, we can use the theorem of Seymour and Zaslavsky. On the other hand, the explicit constructions of them are not so easy in general. And we'll discuss this problem later. And we can consider Fisher type lower bound for the size of X and tight unitary T design. Tight means this equality fold in this Fisher type lower bound. But the classification of tight unitary T designs are still open, and we will not discuss this topic today. Okay. Now, let me quickly review on about irreducible representations of unitary groups, UD. And this is, for example, described in Roy Scott's paper. What I mentioned here can be obtained from this paper. And the irreducible representation of unitary group are parameterized by the non-increasing length D integer sequences. This is integer sequences, maybe negative, integer sequence with this, so non-increasing. So this is equal maybe, but decreasing. Then this integer sequence corresponds to an irreducible representation of UD. And this integer sequence, namely this irreducible representation, the degree of the representation is given by this formula. So this is explicitly known. And in particular, if we take 1, 0, 0, 0, this is natural representation of degree D in D-dimensional Euclidean space. Okay, now let V be the D-dimensional complex vector space and on which UD act. And then this is dual space, namely complex conjugate space. Then the irreducible representation of UD appearing in this tensor product of representation are those mu are non-decreasing integer sequence with sum of mu I, these numbers is R minus S, and sum of those positive numbers mu I, namely mu sub plus, is at most R. So those irreducible representations appearing here are described. And dimension of polynomial space we discussed before, whom UDRS is given by this sum, capital D, small d, RS. This is the sum of squares of degree of irreducible representation which satisfy these conditions. So and these numbers, D, RS, here are 1, 1, 2, 2, 3, 3. These are actually described by these numbers very explicitly. And these numbers give the lower bound for Fisher type inequalities. Namely, Fisher type lower inequalities for unitary T design is if X is a unitary 2E design, then size must be bounded below by this number. This is approximately d to the power of 4 times E divided by this constant. This is E factorial times squared. And if equality holds here, it's called tight unitary 2E design. And similarly, for odd T, we can define Fisher type lower bound and also tight T designs. However, the classification of tight unitary T designs is still open. Namely, it's not clear whether there exists any example at all or not. And also how Fisher type inequality is close to the reality. How real bound is away from Fisher type lower bound is still completely open problem now. Okay. And next stage. Now, we want to discuss the classification of unitary T groups. We are discussing T designs, but T groups first. And as we discussed, unitary T design in UD exists for any T and any D. But the explicit constructions are very difficult in general. So let me start with the discussion of unitary T groups. If a unitary T group, if a unitary T design X is itself a group, so finite set, and if it is also a group, then such X is called a unitary T group in UD. Okay, we sometimes write X by G because so that it makes sure it's a group. And let chi be the natural representation of unitary group of degree D. It is known that G is a unitary T decomposition of this T tensor product of chi into the irreducible representation of G is the same as the decomposition into the irreducible representation of U of D. Now, this condition is equivalent to the condition that expressed by value of characters of group G. And this quantity is same as this quantity. This is equation is matrix equation. I'm sorry, this is numbers because we have an absolute value here. And this is one equivalence condition of G's unitary T groups. And this is considered as a moment on G. This is considered on the unitary group, So it's on the two times T's moment of G and 2 times T's moment of UD. And these moments are expressed as inner product of characters. T's tensor product of chi of G, and also this is on over unitary groups. So these moments or character values are the same over G and over UD. And this is same equivalent to that condition. Decomposition of the related character chi T's tensor product is same over G and over UD. And this is the equivalent condition of G. Group G is a unitary T group. And one remark is when D equals 2, there are some unitary 5 groups. For example, we take SL25. 5 is prime field of 5 elements. So of determinant 1, SL2 by 2 matrix, SL25 of order 120 gives a unitary 5 group. And on the other hand, there is no unitary 6 group in U2. And in physics community, it seems that for some D, at least 3, some unitary 3 groups were known, one family and several sporadic examples. See the list in the next page. But no unitary 4 group in UD were known for any D at least 3. This was the situation in physics community. The following unitary 3 groups have been known. One interesting example is the Clifford group. This group will appear in Dajiao's talk, in the next talk. But anyway, this is a very complicated structure. This is Z4, cyclic group of order 4. This is a central product with extra special group of positive type of order 2 to the 1 plus 2m. So this is very big 2 group on which SP2M2, this is symplectic group over binary field to 2m dimensional and over F2 act on this big 2 group. And this very particular Clifford group is known to be a unitary 3 group in U of dimension 2 to the power of m, but cannot be a unitary 4 group. And the following sporadic example of unitary 3 groups for UD has also been known. There are some sporadic examples come from very interesting groups. These are central extensions of, and for example, 6 Suzuki is Suzuki sporadic simple group, central extension by 6 of order 6 cyclic groups, central extension, and for these particular dimensions. These are sporadic examples and one infinite family. And this J3 is a third Yanko's group. And there are some examples of unitary 3 groups, but no 4 groups were known for D at least 3. But we have now the classification of unitary T groups. This was finally done by our joint paper with Navarro, Rizzo, and Teep. Title of the paper is Unitary T Groups, published in Journal of Mathematics Society of Japan about 2 years ago. And this paper gives the following answer. And we pointed out that the paper by Guralnik and Teep, GD, the title of the paper is Decompositions of Small Tensor Powers and Larsen's Conjecture, and published in Representation Theory. This is a journal 2005. Already gave the no-existence of unitary T groups for a T at least 4 and at least D5, at least D5. And so the essential part was already done, Guralnik and Teep. And actually, this was not known in physics community. And also, this was purely finite group theory paper, and actually no relation with unitary T groups or unitary T designs were known at that time. And also, this Guralnik-Teep paper gives the complete classification of unitary T groups in UD for all T at least 2, and if dimension is at least 5. And when dimension D is small, 2, 3, 4, it's slightly complicated. But our paper, actually mentioned here, gave the complete classification of unitary T groups, finishing the remaining case D equal 2, 3, and 4. And this remaining the case of dimension 2, 3, 4, the classification are also very interesting as finite so-called unitary reflection groups, complex reflection groups appear there in a very crucial way. And classification, complete classification is interesting. Anyway, we have the complete classification of unitary T groups if T is at least 2 and T is at least, and D is at least 2. And then how about the explicit construction of unitary 4 designs in U of 4-dimensional unitary group? Can we construct explicitly unitary 4 designs? Because in the physics community, this was kind of difficult to find such examples. This is a first challenging, first interesting case to challenge the problem. So the explicit constructions of unitary 4 designs in U of 4 was not made before. But we could answer this question in a joint paper with Mikio Nakahara and Da Zhao and Yanju. And the title of this paper is on the explicit constructions of certain unitary T designs. And it was published in a physics paper, Journal of Physics A, about 3 years ago. And the rough method is as follows. We get the following theorem. Namely, let chi be the natural representation of U of D. Suppose that G is a unitary T group in UD. And in addition, that the following condition about value of inner product is satisfied. We take chi up over T plus 1. We take this representation, take inner product on G. And we take inner product on UD. Because G is a subgroup of UD, this is usually inner product UD is smaller than this. And if this inner product over G and over product UD is equal, so there is no plus 1 here, then G is a unitary T plus 1 group. But what happens if this inner product and this inner product is just difference just by 1? There are some such cases. In that case, there exists a non-trivial, unique up to scalar multiplication of polynomial f over ud of degree t plus 1, which is invariant by the action of G cross G. This G cross G group act on UD very naturally. So if this condition is satisfied, then we can see there is a unique non-trivial F here, and we can calculate this. And this is a function on UD, and let x naught be any zero of this function f. And there is a guarantee that such x naught exists, and we can find them explicitly. If we find such a zero of x naught by the action of G cross G on UD becomes a unitary T plus 1 design UD. So if this condition is satisfied, then from a unitary T group, we can get unitary T plus 1 design. So this is a general result, but we apply this. So in our paper by Bannai, Nakahara, Zhao, and Yanju, we could show that we had a unitary 3 group SP43. This is a symplectic group, not simple. That has a center of order 2. This has a 4-dimensional representation, complex representation. We had a unitary 3 group, and this unitary 3 group satisfies the previous condition. So based on the previous theorem, we can explicitly construct unitary 4 designs in U of meaning of explicit construction is we can describe such examples numerically with the errors as small as we want. Actually, we have the guarantee of the existence of unitary 4 design on U4, and we can find their explicit values as precise as possible as we want. However, such examples are very big, sizes are very big. The size of the smallest unitary 4 designs in U4 thus obtained is actually this big number now. And this is a bit away from Fisher type lower bound, but we really don't know how much we can reduce these bounds. Okay, anyway, unitary 4 designs in U of 4 were constructed. Now, this is a main result of our main result, namely, we want to discuss explicit construction unitary joint work with Nakata and Okuda and Dajao. And this is put on archive. This is an archive number. We submitted this paper, but it's not yet published. And our main theorem is for each pair of T and D, for any T and D, we can explicitly construct unitary T designs in U of D. So we answer the question of explicit constructions. And here is the idea of the proof. We use induction on D. This is our basic point. And in order to use this induction, we need to introduce some new concept called strong unitary T design in UD. This concept of strong unitary T design is stronger than ordinary unitary T design. But to use induction, we need this concept. And another important thing, law of U of D, or any compact group G. We say that a subset X in UD is a row design. Row is any representation, row design, if this condition is satisfied. And this is an integral over this Lie group G. In this time, unitary group UD is same as this finite average value of at X, at finite set X of rho. If this condition, I write star, is for any representation, we say such X is a row design. It is defined for any irreducible representation of G. As we discussed before, irreducible representation of UN, sorry, this time we use slightly different notation, N, are parameterized by non-increasing integer sequences, lambda equal lambda 1 to lambda n. This is non-increasing integer sequence. As before, let lambda sub plus be the sum of positive lambda i's and lambda minus be the minus of the sum of negative lambda i's. So lambda plus lambda minus are non-negative numbers. And we introduce the subset of lambda. Lambda is non-increasing integer sequence. This is phi of ntt. N is dimension, tt is those integer sequence lambda, such lambda plus this value is same as lambda minus, and this is at most t. On the other hand, we define psi sub n tt is a set of lambda integer sequence such that lambda t is at most t, and also lambda minus is at most t. And we define finite set X in UN to be a strong unitary T design if the equality star hold for any irreducible representation rho sub lambda appearing in this set. And also, please recall that finite set X is an ordinary unitary T design if the equality of star hold for any irreducible representation rho sub lambda in this phi sub n tt. So there is difference between strong unitary T designs and ordinary unitary T designs. But please note that from these definitions, phi sub n is subset of psi n. Of course, this is psi is bigger. And this implies, by definition, that a strong unitary T design is a unitary T design. Okay. And then we want to use kind of induction. Let G is a unitary group of N, K is a subgroup, UM times U of N minus N. Then so-called G over K is so-called Grassmannian space, GMN. And in particular, if M is equal to 1, then it is a complex projective space. And we use induction, so we can easily construct strong unitary T designs in U sub U of 1. We can have just set of primitive T plus first root of unity gives an example. I'm sorry, gives you the root T plus 1 root unity. I'm sorry, but we can construct strong unitary T design U1 easily. Now, let X sub M be a strong unitary T design in UM, and X sub N minus M be a strongly unitary T design in U of N minus M. Then we consider subset XM N minus 1 of this form. G is from XM, H is from X N minus M. This is a subset of U of N. And we can see this is a rho lambda design in this product group UM cross UM, namely rho design for any irreducible representation rho appearing in this representation. But anyway, we have for such rho lambda, we can get this subset becomes this design. Now let F1, F2L be all the so-called zonal spherical functions of this homogeneous space, G over K. And there are only finitely many zonal spherical functions as a basis. And let xj be a zero of fj. We can find zero for each spherical function for each j equal 1 to 2, 1 to L. Then we can canonically find element gj in G such that the action of gj on G is the same as Vj. And okay, Gj is an element in unitary group such that the action on G over K is the same as this Vj. Vj was 0 over Fj. And in this situation, we take new subset X, maybe X sub n, is X as a product of finite set. xn minus a is finite set, and Gj is one element of unitary group of degree n. And this finite subset, and this is finite subset, and take all product of these finite. Then this gives a set in the unitary group. Actually, there is a possibility of some element here may have multiplicities. Namely, exactly speaking, this is a multi-set. But in that sense, this set becomes a strongly unitary T design in UD. So here we can, this set becomes, we can show that strong unitary T design. So we can complete induction starting n equal, actually n equal 1, n equal 2, and so on. By using m equal 1, we can use induction. Hence, this gives explicit constructions of many unitary T designs U of D for any T and for any D. So by this method, we can complete the explicit constructions of unitary T designs in UD. And I mentioned at the beginning, we had construction of unitary 4 designs in U of 4. And in that case, we had some invariant polynomial, and we consider 0 and take orbit. And the situation here is kind of extension of that method. So we got the following theorem that for each pair of T and D, we can explicitly construct unitary T designs in U of D. And one remark is this idea also gives explicit constructions of spherical T designs in Sn-1 by induction on N, namely by using real orthogonal group On instead of Un. But the proof is very similar. Anyway, we can have an explicit construction of spherical T designs by induction on N. Now, finally, there is one remark. Our theorem was already applied to experimental physics in quantum information theory. And for this, please see the following paper. The title of the paper is Quantum Circuit for Exact Unitary T Designs and the Application to Higher Order Randomized Benchmarking. and this already published in Quantum Information Journal, PRX Quantum 2, and this is last year. And this paper in experimental physics. So we have many authors. And first author is Yoshifumi Nakata. This is, and Da Zhao and Takayuki Okuda and myself. This is the whole of the other authors of this paper. And other papers, other authors, there are actually total 12 authors. There are experimental physicists. And I really do not know the exact content of this joint paper, but this paper actually is using our result of the explicit constructions of unitary T designs. And I think explicit constructions of unitary T designs are very useful in physics, and I expect there are many, many applications. Okay, thank you very much. This is the end of my talk.
Okay, thank you very much for your talk. Are there questions to the speaker?
Yeah, I have a question.
Okay, Alexander, please.
Well, maybe some question, please. I want some remarks.
Okay.
Okay.
First question, please.
Okay, then I have a question.
Oh, yes.
So the remark before the final remark, you mentioned spherical construction of spherical design.
Yeah.
Yeah, so the unitary design is a finite subset of UN, but spherical designs are not finite subset of ON. So there's some difference.
Difference actually change.
Yeah.
Similar kind of take subgroups, and we must consider representation of ON. And we can repeat what we did. In that sense, this is very similar. This is not immediate from this result.
But then you end up with a finite subset of ON.
Yes, and take element and take the action of element in unit sphere and take the orbit, then it becomes spherical T design.
I see. Okay. Thank you very much.
Thank you very much.
Questions?
Yeah.
Okay, then comment from Alexander.
Professor Bannai, first of all, thank you very much for extremely interesting lecture. The subject of this lecture was in some sense surprising for me, because in my mind, this subject was a part of the functional analysis. But now I understand that it's very, very nice algebra. So it was just something new for me. But I should say the following. Some participants of our conference are coming from the Sobolev Institute of Mathematics. Sergei Sobolev was, of course, greatest mathematicians. Most of his works were devoted to the differential equation and also to embedding theory. But the last part of his life, he spent exactly doing this subject from the point of view of functional analysis. His name was, of course, Kubatur formula, slightly different from you, but you mentioned it in the beginning.
Yes.
Yeah, he wrote a few books. It was exactly the time when I was as a student. Of course, the result obtained by Sobolev has a lot of application in the functional analysis first. And then that is also very important. The embedding theorem play important role in the discrete mathematics. When we have to calculate some discrete functions, again, we have used this embedding theory. And the result you mentioned in your lecture, of course, can be implied for this part of mathematics as well.
Yes.
So thank you very much once more. It was a great pleasure for me to hear your lecture.
Okay, thank you very much. I know the work of Professor Sobrev, and it really related to this topic.
Yeah.
Amazing. Okay, any other questions? Well, I just have one small question about applications. So you said that it is applied to physics, but are there any other applications in physical research, not only in quantum information? Yeah, difficult.
Yeah, I really don't know.
Okay.
Applications of physics, but I'm pretty sure that this has many applications, and many people actually in physics want explicit construction, and
Right.
they are usually very difficult to explicitly construct exact unitary groups, and usually they are satisfied with approximate designs, but
Right.
explicit one will help very much.
Right, exactly, yeah. Okay, thank you very much. Let us thank again Professor Bannai for this great talk. It was really nice to have this talk. Thanks a lot.